Add 30 milliliters of 3 molar sodium hydroxide. We interrupt this broadcast of
Science-y Time with Noah and Jerry
to bring you
Chemistry and Crumpets. Welcome! Today we'll be performing an experiment entitled The Synthesis of an Ion Coordination Compound. The purpose of this activity is to prepare iron oxalato, which will be used in future lab procedures. Let's get started, shall we? First, into a clean 100 milliliter beaker, transfer 16 milliliters of stock solution containing 0.4 grams of iron chloride per milliliter. Next, weigh out 24 to 25 grams of potassium oxalate monohydrate and transfer it to a clean 100 milliliter beaker. Afterwards, add 40 milliliters of deionized water to the potassium oxalate monohydrate. Now, heat this solution while stirring until the solid is completely dissolved. If you're anything like the blokes shown here, your solid might never dissolve because you added 20 milliliters of water, not 40. Nice try, you blithering nincompoops. At any rate, make sure there are 40 milliliters of water in the beaker. Also, a magnetic stirrer is a much more efficient way to stir, and your solution will be clear in no time. After that, pour the hot solution into the beaker containing iron chloride. Once mixed, the new solution will suddenly turn green. Keep stirring, chaps. Now, remove the magnetic stirrer if you used it, and secure some parafilm atop the beaker. Now, fill a large styrofoam container with ice, and place the beaker inside of it for 30 to 45 minutes. When you remove the beaker from the ice bath, some crystals will have formed. Now, pour off the liquid without removing any of the crystals. Don't worry, the crystals will not easily come out of the beaker. Now, we are going to perform the crystallization process yet again so as to purify the crystals. First, add 40 milliliters of water. Heat the solution and stir once again until the crystals are completely dissolved. Now, as before, remove the magnetic stirrer, secure the beaker with some parafilm, and place it in an ice bath for 30 to 45 minutes. Yet again, some crystals will form. Now, weigh a piece of filter paper and place it in a Buchner funnel using deionized water to secure it in place. Turn on the sink to start vacuum filtration and pour the contents of the beaker through the filter paper. As the crystals are being sucked dry, prepare 2 5 milliliter portions of ice water and 2 5 milliliter portions of acetone. Wash the crystals twice with ice water, and then do the same with acetone. Once the crystals finally appear dry, remove the filter paper and place it on a watch glass. Store this overnight to ensure that the crystals dry out completely. Afterwards, weigh the filter paper and the crystals, subtract the weight of the filter paper, and determine just how much solid was produced. Last but not least, transfer the crystals to a dark bottle that shields them from the light and store them for future experiments. Now, you're probably asking yourself exactly what reaction occurred in this experiment. Well, it's quite simple actually. Potassium ions, iron ions, oxalate ions, and water all reacted to form iron oxalato. The problem is, we know very little about iron oxalato at this time. Until we perform future experiments, we won't know how much potassium, oxalate, and hydrate the compound contains. Right now, all we know is that each molecule has 1 atom of iron. Now, let's examine this experiment's pre-lab questions. In this experiment, you will react an aqueous solution containing 3.20 grams of iron chloride hexahydrate, which is 270 grams per mole, with an aqueous solution containing potassium oxalate to produce the product iron oxalato. Number 1. Assuming that all of the iron originally in iron chloride hexahydrate ends up in the product iron oxalato, how many moles of product should be obtained? Well, through a simple stoichiometric calculation, it was determined that 0.012 moles of iron oxalato should be obtained. Number 2. What additional information would you need to calculate a percent yield? Well, once the crystals are obtained and weighed, they cannot be compared to the theoretical yield, unless the theoretical mass of the crystals is known. We would need the molar mass of iron oxalato to convert the theoretical yield in moles to the theoretical yield in grams. And now for the results. 15.99 milliliters of the iron chloride solution were originally used. Given that it contained 0.400 grams of iron chloride per milliliter, that means that 6.40 grams were used. As for potassium oxalate, 24.5582 grams were used. The filter paper weighed 1.0002 grams, and the filter paper with the crystals weighed 6.5943 grams. Thus, the total mass of the crystals obtained was 5.5941 grams. Now, sadly, there are a number of ways in which some of our beautiful crystals may have inevitably been lost. So, without further ado, let us discuss this experiment's sources of error. First of all, cooling the solution in an ice bath was meant to decrease the solubility, causing the crystals to come out of solution. However, as suggested by the greenness of the solvent even after the cooling process, this decrease in temperature was not enough to cause all of the iron oxalate to precipitate. Thus, during the decantation process, some of the potential product was unavoidably lost. Similarly, the crystals were washed with cold water so as to decrease the likelihood that they would dissolve. Nonetheless, the greenness of the filtered fluid indicates a loss of product. Of course, there are also many instances in which minor amounts of the product may have been lost. For example, traces of the solution may have been left behind on the stirring rod when it was removed, or on the beaker when it was emptied during vacuum filtration. Thank you for joining us for today's installment of Chemistry and Crumpets. We hope you enjoyed this presentation.